5.2, the definite integral. So first, just remember from our last section that we were saying that we could compute an area or try and find the distance traveled by an object given a velocity using this limit of the sums of all of these little rectangular strips. So here we're just saying let's sum up all of the rectangular strips, and this is the height of the strip and this is the width. In other words, let's do height times width plus height times width plus, and so forth. So this is just saying, let's do the summation, and here's just writing it all out. So just to put it more formally, the definition of a definite integral. If f is continuous, okay, it's continuous, and it's defined on some interval between a and b, we're going to divide that interval into n subintervals of equal width, and we're going to make the width of each of them, the delta x, the width of each of the intervals, b minus a over n. We're going to let x sub 0 equal a, our beginning, and then we're going to just put all these little x's in between, the n subintervals, and the last of them would be our other endpoint, b. And we just say let x1 star, x2 star, up to xn star be any points in those subintervals. It doesn't matter if they're left endpoints or right endpoints, pretty much. So then we say the definite integral, okay? And the definite integral, we'll talk about this more later, but the definite integral means it's defined from some a to b, okay? That's what makes it a definite integral. And we say the integral from a to b of f of x dx, because we're taking the integral with respect to the variable x. So that's what the dx is for. So basically whatever's in between is what we're taking the integral of, equals the limit as n goes to infinity, as we make infinite number of little strips of these height times width rectangles here. So we're just adding up all the rectangles to approximate the area under the curve. And as n goes to infinity, we're going to get the area under the curve. Because f is continuous, the limit in this definition always exists and gives the same value no matter how we choose the sample points, x sub I star. Doesn't matter we use left, right, or midpoints, because we're choosing so many of them, it gets so tiny, the width of our rectangles. So just more notation, the squiggly, okay, the squiggly is called the integral sign. F of x is an integrand because it is what we're finding the area of under. Basically, we want to find the area under the f of x curve. So this right here is our integrand. Okay, it's saying take the integral from a to b of f of x with respect to x. Okay, so that's what the dx is. Basically, if we had f of t, then you would want to do dt. If you had f of r, you would want to do dr. Just like when we're doing dy dx, it meant, remember, dy dx, it meant take the derivative of y with respect to x. So here's just formalizing it with what variable we're taking the integral with respect to. A Riemann sum is just adding up all these rectangles to approximate the area under the curve. If the function happens to be positive, then the integral from a to b of f of x dx can be seen as the area under the curve y equals f of x from a to b. If f takes on both positive and negative values, then the Riemann sum is the sum of the areas of the rectangles that lie above the x-axis, and then you subtract out the rectangles that lie below the x-axis. So figures 3 and figure 4 shows it really well. It's just a net area. So far we have defined the integral from a to b of f of x dx by dividing our interval from a to b into subintervals of equal width. But sometimes we would prefer to work with subintervals of unequal width, and that's okay. We just have to ensure that all of these widths that we are picking are approaching 0 in the limiting process, because basically what we saw last time and what we've seen this time is that we want to make an infinite number of rectangles under this curve. The more rectangles we make, the better approximation we get. And so if we make this width of our rectangle infinitely small, And that's what we're trying to say. Let the delta x go to 0. Let the width of our rectangle get so teeny tiny. Then we're going to get the exact area under that curve. Here, we just want to write the sum as an integral. So since we're doing the limit as n approaches infinity of this sum, what are we doing? We're going from the interval from 0 to pi. What's our function? It's just x cubed plus x sine x. The reason it says x sub I is because we need to take all the little subintervals, but our function's just x cubed plus x sine x. If we're looking at some point, x sub I, we just plug that in, right? Like if I wanted to do f of 3, I would have plugged in 3 everywhere. So here they're just saying, well, let's plug in some x sub I. So that's why it says x sub I cubed. And what are we taking this with respect to? With respect to x. So that's it. That's all you have to do. In order to evaluate integrals, we're going to need these formulas. You'll see why they're useful. You don't need to memorize them. So let's go ahead and evaluate this Riemann sum. Let's just do it the way we were doing in last lesson. So we want to use right endpoints, and we want to go from 0 to 3, and we want 6 rectangles. So we're going from 0 to 3, and we want 6 rectangles. So delta x is going to be 1/2. So 1/2, 1, 3/2, 2, 5/2. And we wanted right endpoints. So here's our first one, here's our second one, here's our third, fourth, fifth, and sixth. Remember, this is our rectangle, so this would be the right endpoint. Okay, and the width of our rectangle is 1/2. So in order to evaluate this, we're going to do the width times the height. So the width is 1/2, and the height of our first one is the function value at 1/2 plus the width times our height, and the second endpoint is at 1. Width times height, and so forth. As you see here, if we do have rectangles all of equal width, you could have just factored out the 1/2 originally, if you saw that. If not, it's no big deal, just write it out. Might have been easier to write this. Then I'm just going to stick this all in my calculator. I'm going to put in y1, x cubed minus 6x, and then I'm going to go to the home screen, and I'm going to type all that in. So I'm going to type in 1/2 times y1 of 1/2 plus y1 of 1 plus so forth. And you should get negative 3.9375. Now another approach, if we can look at the function as a shape that we're familiar with and we're familiar with the area of, then we should do so. For example, you know the function, and you should know this function very well. If I give you y equals the square root of 1 minus x squared, you should be able to immediately, okay? And if you can't right now, then you've got to be able to immediately recognize that is the upper half of a circle, because you know that x squared plus y squared equals r squared is a circle. So you know that this is the upper half of a circle with a radius of 1. Here in this case, we're only going from 0 to 1. So this would have looked like this whole shape here, the whole top half, right? Because we would have split it into plus and the minus would have been the bottom half of the circle. But we're just going from 0 to 1. The x is going from 0 to 1. So the x is going from 0 to 1. So we only have a quarter of a circle now. And what do we know about the area of a circle with the radius of 1? Well, that would have been pi r squared, which would have been pi times 1 squared, just pi. But what do we want? We want a quarter of a circle with radius of 1. So 1/4, the area, is just going to be pi over 4. Therefore, the integral from 0 to 1 of the square root of 1 minus x squared dx is just pi over 4. That's it. Similarly, if we have a function y equals x minus 1, that's real easy to draw. We can draw it in. We want to go x values from 0 to 3. So just draw this from 0 to 3. And so what do we have? Well, what is area of this guy? Well, the width is 2 and the height is 2. And so A1 is just 1/2 base times height, just going to be 2. And here, width is 1, the height is also 1. And so the area is going to be what's above the x-axis minus what's underneath. Okay? And so the integral from 0 to 3 of x minus 1 dx is just going to be just that. The midpoint rule. When the purpose is to find an approximation to an integral, it's usually best to choose a sample point xi to be the midpoint of the interval. So not left, not right, but the midpoints, and we're just going to denote that as x sub I bar. Okay, put the bar on top. Just notation again. So now when we're approximating this, instead of saying f of x sub I, we're just going to say f of x sub I bar. And what is x sub I bar? It's just 1/2 of the left plus the right endpoint in the middle of the two. So in this example, we want to evaluate the integral from 1 to 2 of 1 over x dx with 5 rectangles. So we're going from 1 to 2, and our delta x is going to be 2 minus 1 over 5, because we're splitting into 5 intervals. So it's just going to be 1/5. So I'm going to go 1, 1.2, 1.4, 1.6, 1.8. And then I want midpoints. So I want in the middle of each of these rectangles. So here's the first, second, third, fourth, fifth. And since, I have a function here, I have all this data. So the first midpoint is going to be at 1.1, then 1.3, 1.5, 1.7, and then 1.9. So in order to evaluate the integral, I'm going to add up the area of all these rectangles. So the width is just 1/5, and the first midpoint is f of 1.1 plus 1/5 times f of 1.3, and so forth. And if you could see there that you could have pulled the 1/5 out originally, you could have done that without having to write so much. Probably would have been better. Sorry. And then if you just put this all in your calculator, like I showed in the last example, you should get 0.6919. So some properties We can define the integral from a to b even if a is greater than b. So meaning even if, I have some function and I say, all right, let this be b and let a be greater than b. Well, then I can say that the integral from b to a of f of x dx, so the integral from b to a is just that, is the same thing as the opposite the integral from a to b, because I would be going backwards. If a is equal to b, then I'm saying what is the area under the curve from a to a? Well, that would be nothing at all because my width is just 0. So the area of my rectangle would just be 0. So some properties, if we have just a constant c here, then the integral from a to b of c dx is just c times b minus a. Because this is just the height and this is just the width, because pretty much I just have a rectangle, because I'm saying, well, let my function be some constant c, okay? And so what is the area under my curve from a to b? Well, it's just that. So it's just a rectangle, c times b minus a. Nothing tricky, fancy there. You can push the definite integral through, just like you could push a summation through. You could take a constant out, just like you could take the constant out of a summation. You can push it through a difference also. So this is just illustrating one, and it's just illustrating the sum. So let's just use the properties of integrals to evaluate this. So basically we can push that integral through. You can pull the constant out. All right. And then what do we know? We know that the integral from 0 to 1 of 4 dx is just 4 times 1 minus 0 plus 3 times, and I'm just going to tell you this integral for now is 1/3. Don't worry about why. I will show you why. That's it for now. Another thing that we want to note is that if we take the integral from a to c and we add the integral from c to b, and c is some point between a and b, that is just going to be the same as integral from a to b, okay? Because you're just adding up the two. And this is a typo, so please change this on your PowerPoint. The question should read like that. If we know that the area under the curve from 0 to 10, so from 0 to 10, the area is 17. The area under the curve is 17. And we know from 0 to 8, the area under that curve is 12. Then what is the area under the curve from 8 to 10? Well, that's just going to be whatever the area from 0 to 10 was, minus, okay, the area from 0 to 8. You clearly see that it should be 17 minus 12. That's it. So we know that the integral from 8 to 10 of f of x dx is 5. Some comparison properties. If f of x is greater than or equal to 0 for all x's between a and b, then you know that the area under the curve is positive because it's always above the x-axis. If f of x is greater than g of x, then you know that the area under the curve of f of x is going to be greater than the area under the curve of g of x. And the last one is tricky to look at, but it's another one that's obvious if you look at the picture. So here we're saying that some m is less than f of x. So we don't know the f of x curve. But let's just say m is a constant, okay? And m is always less than our function. And our big M is always greater than our function. So the value of big M has to always be greater than any value in our function. It has to be bigger than the greatest max. And the little m must be less than our smallest minimum. Well, then what do we know? We basically know the area of this dark purple, okay? And that's the area of our dark purple region there, right? Because it's just the height times the width, b minus a. We know that is less than or equal to the area under our curve. So the area under our curve is actually the whole thing here. Red hash marks that I just did represent this area that I'm talking about here. And I know that's less than or equal to the area of my big box. So this is the small purple box, this area. This box is the shaded one that I did. And then this is just that big box there, the area under that whole box. Okay, so how do I use that? I might use that if I want to estimate the area under the curve of some function that I don't really know that much about, but I do know some limits. So let's just think about this curve. Y equals e to the negative x squared. And I want to go from 0 to 1. Okay, so what is my value f of x? My f of x that I'm drawing is just e to the negative x squared. F of 0, e to the negative 0 is just 1. And f of 1 is just e to the negative 1, which is 1 over e. So I now have 2 points, and I know more or less what e to the negative x squared should look like. So I have a point here, 0, 1, and I have another point here, which is 1, 1 over e. Okay, and I know kind of what the shape of the curve looks like. I know what y equals e to the x looks like, and this is y equals e to the negative. So it's pretty much what it's going to look like. Now, how might I be able to use that last slide to do something? So I know the area under my curve is bigger than that, but smaller than this. And so the area of the big one, let's call that big M since that's kind of the notation from the last one, was just the width times the height. The area of this small one here is the width times the height, and the height of this is just 1 over e. So what do I know? I know that a little m is less than or equal to the area under my curve, which is less than or equal to the area of that big M. So I know 1 over e is less than or equal to the area under my curve, which is less than or equal to 1. And I might just want to evaluate that so I have more of an idea. And that's pretty much all I know. Now, I'm asking you to just evaluate this. Our delta x, this is the same problem, is just 3 minus 0. But now I don't know how many rectangles I want to divide this into. I want to divide it into n rectangles. So I get 3 over n. Meaning, if I'm using right endpoints, then my first little xi, okay, the first right endpoint that I choose is going to be 0 plus whatever the width is. Okay, the first one would just be 0 plus 3 over n. This would just be 3 over n. But then the next one would be 3 over n plus 3 over n, and so forth, right? So we just take our endpoint 0, that comes from here, plus the delta x. And the ith one is just delta xi. And so we can say that this can be approximated as the limit as we get infinite number of these little rectangles. Okay, we're summing up all of them. Okay, and what is the height? The height is just this, but we're going to evaluate it at xi. Okay, the xith one. So xi cubed minus 6 xi, and our dx is just 3 over n. And what is x sub I? Our x sub I is just this, 3i over n. Keep going. Now I can factor this 3 over n out of the summation because it doesn't have any I in it. I can't take it out of the limit because it has an n in it, but I can factor it out of the summation. So I'm going to do that. Okay, so what do we have? I'm going to just push the summation through. And I have to distribute, of course, the 3 over n. Okay, so I'm not doing anything fancy here. I'm just doing algebra. I'm just basically, because it was a summation of this whole thing. And so I need to distribute that. Now I'm going to just multiply this back in. So 27 times 3 is 81. And n times n cubed is n to the 4th. And then 3 times 18 is just 54. N times n is n squared I. And then we have the limit as n approaches infinity. I'm just going to take this out. This doesn't deal with I, so I can take it outside of the summation. And I know that the sum from I equals 1 to n of I cubed, go back, that's just this right here. So I'm going to just use that. Then I have, let's see, 3 times 18 is 54. And the summation of I was just this guy. And so now I just need to do some algebra. Well, I'm going to do n squared times n plus 1 squared all over 4. And I can do that because I don't have any plus signs there. I'm just multiplying. Okay, so what do we have? (81 over 4). I'm going to just put all the n stuff together. And then, let's see, I have n squared, n plus 1. So just rearranging. So that I can simplify. Oh no, I made a mistake. This was n squared. This should have been n squared, n squared, n squared. Okay. 27. Then what do I have? I have an n plus 1 over n. And so I'm just going to, since it's squared, I'm just going to write it like this because I'm squaring the top and the bottom. And so, oh boy, what happened to my 81/4? There it is. Just going to rewrite on the next line. And so here I have a 1 plus 1 over n squared minus 27, 1 plus 1 over n. And I want to, as n goes to infinity, so as n goes to infinity, 1 over something huge goes to 0. Sticking in, n goes to infinity. So I'm left with negative 6.75. Okay. Not so easy. Just a lot of algebraic manipulation. Not really using that much calculus there. You won't have to do too many of those problems. That's a good news. But you do have to be able to identify a problem like that. And note that our approximation in our last slide was not too off. And we only used, 6 rectangles there. So good check. Here's just showing what the graph looked like. So remember, you were subtracting out the blue region and you were adding in this peach region. And that's the end of this lesson.